Find the area of tension steel in inches squared. In this problem, a doubly reinforced concrete beam is subject to a given live moment and given dead moment. The strains and stresses in the tension and compression steel are provided, as well as the dimensions for the depth to tension steel, D, the depth to compression steel, D', and the beam width, B. The Young's modulus of the steel and the compressive strength of the concrete are also provided. To find the area in the tension steel, we'll begin with the axial force equilibrium equation, where the compressive forces in the concrete and steel equal the tensile force developed in the tension steel. We'll write out these variables and solve for the area of steel term, AS. Next, we'll plug in the given variables for the compressive strength of the concrete, lengths A and B, and the stresses in both the tension and compression steel. This makes the area of steel equal to 5.343 inches squared plus 0.942 times the area of compression steel, AS'. To find the area in the compression steel, AS', we'll take the moment about the tension steel, where the nominal moment, Mn, is at least the ultimate moment experienced by the beam, Mu, divided by the strength reduction factor, B. The ultimate moment equals 1.2 times the moment caused by the dead load plus 1.6 times the moment caused by the live load. The problem statement provides these moments, and after they are substituted in, the ultimate moment experienced by the beam equals 5.72 times 10 to the 6 pounds-inches. This value is substituted in for the ultimate moment, Mu. And now we are left to compute the strength reduction factor, Phi, which is a function of the strain in the steel, epsilon s, and the yield strain in the steel, epsilon y. From the problem statement, the strain in the steel equals 0.004. The yield strain in the steel equals the yield stress in the steel, Fy, divided by the Young's modulus of the steel, Es. The problem statement also provides these two values, and the yield strain in the steel computes to 0.00207. Returning to the chart to determine the strength reduction factor, Phi, we can linearly interpolate to compute the value of Phi. After plugging in the appropriate strain values, the strength reduction factor equals 0.815. Now we'll plug this value into the equation for the nominal moment, Mn. And the nominal moment is at least 7.018 times 10 to the 6 pounds-inches. Since we don't want to over-design the beam, we'll change the atmos sign to an equal sign. Now that we have the nominal moment in the beam, we can solve for the other variables in the moment equilibrium equation. Keep in mind, we're trying to solve for the area of the compression steel, As', in order to ultimately solve for the area of the tension steel, As. The term which contains the area of compression steel is variable Cs, the compressive force in the compression concrete, which equals the area of compression steel times the stress in the compression steel. The problem statement provides the stress in the compression steel equals 56,500 pounds per square inch. So we'll leave this term as a function of the area of compression steel, As'. The problem statement also provides the depth to tension steel, D, the depth to compression steel, D', and the length, A. The last variable to compute is the compression force in the concrete, Cc. The compressive force in the concrete equals 0.85 times F'C times A times B. The problem statement provides these three values, and the compression force in the concrete computes to 3.206 times 10 to the 5 pounds. At this point, we can substitute all the variables into the moment equilibrium equation and solve for the area of compression steel, which equals 1.78 inches squared. Now we are ready to solve for the area of tension steel by plugging in AS prime. The area of the tension steel equals 7.02 inches squared. When reviewing the possible solutions, the answer is D.